I talked about the frequency in mels and frequency in hertz, right? So there is a unique relationship, a pretty good relationship, and this relationship is given, people have fitted a curve. This is called the Mel curve. So this is the relationship between capital F, which is a physical frequency, and Mel, which is a perceived frequency, okay, the pitch, right, the perceived frequency. So similarly, intensity is a physical quantity, loudness is a perceived. How loud is it? It's something that I perceive, okay. So these are used sometimes interchangeably, but that's not correct. One is a physical quantity, the other is a perceived quantity, okay. Similarly, frequency in hertz is a physical quantity, pitch in mels is a perceived frequency, okay. So I was talking about this idea of masking, and that's very important. In the ear, what happens is, if I have a frequency which is dominating, let's say 1000 hertz, right? Around that frequency, we have something called a masking curve, okay? So what happens is, if this is the dominant frequency, which I've plotted with an arrow with a long, it has got a large magnitude, so it is very strong tone. Let's say it's a 1000 hertz tone. Then if I have another tone at, let's say, 1200, right, and its amplitude is only 0.7 or something, and this is at 800 and it's at 0.6 or something, right, these two guys, even though they are physically present in the signal, you will not hear them. You will hear only, it will look like a pure tone. So surprisingly, if I have three frequencies, right, 1000, something at 800 and something at 1100, let us say, I will not hear all the three frequencies. If you ask the ear, and if this is dominant, depends of course on the relative amplitudes of these three. So if the 1000 tone is dominating, has a high value, right, energy, right, even though the other two are there, you will find absolutely no difference between just playing the single 1000 hertz tone and playing all three. To the human, because of the deficiencies of the ear, because of the masking property of the ear, the other two sounds are not even heard. It's as if they did not even exist, okay. And that is the principle on which the MP3 players act. So if these are physical frequencies that are present in the signal, but something that the ear cannot sense, might as well make them zero, right? Why even carry that information? So you zero it out, okay. I mean, I'm giving a very crude way of doing it. It's very sophisticated algorithm, right? But the basic idea is this, that you don't have to capture all this information, so you can zero it out. If I am having sparse, with lots of zeros, then there are very efficient ways to code it, and that's how your MP3 players are able to get, very good quality, because they are, zeroing out elements that are not perceived by the ear, right? And but is the original signal and the MP3 signal same? No. The MP3 signal has lost these pieces of information. These were there in the original signal, but it's not there in the MP3 representation, okay. But whatever it has lost, it's a lossy process, okay. Whatever it has lost is something the ear anyway was never even sensing it. So why carry it along, right? So you throw it away, right? You don't need to capture it or store it or transmit it, right? And that's the basic idea of MP3. That's how you're getting very good bit rates with quality that's almost like CD, okay. This is called frequency masking. Surprisingly, you also have the concept of time masking, right? So if something happens before, if a strong happens and something weak happens before, that's called pre-masking, or if something strong happens and afterwards something weak happens, relatively, depending on the amplitudes, the weaker one will never be heard. And even so, you can see that it's not like, perfect real time. Even we don't operate in perfect real time. We take some time for the transmission of everything to go up to the brain and for it to process. It does not immediately react to every one of the sound signals that it gets. So, and the reason is, the ear is trying to protect itself from the stupidities that human beings might do. So just to give you an example, if I drop a pin in isolation, right, in a quiet room, you will hear the pin, okay. And then if I play, if I stand next to a jet engine, let's say jet engine is very close to me, I'm sitting here, and if I ask the pilot to start the engine, whoo, big jet engine sound will come, okay. My ear can handle both of these high difference in dynamic range. This is a very soft signal, still it will pick up, and I'll sense it in the brain. And then when the jet engine goes, it will still hear that, but now my ear, actually the eardrum and everything will tighten up, so that or actually it will loosen up, sorry, so that the vibrations are not very big, right? So because rarefactions are going to come, it will keep itself. So if you keep a very loose, a tight balloon means it will vibrate fast. But if you keep loose, it won't move much, right? So the ear is protecting itself from all the damages that you might be, in a rock concert. That's why it is trying to help itself by, even though you might abuse it. Okay, but now suppose I am doing a pin drop, and then within a few milliseconds I switch on the engine. Okay, you would think that I can hear the pin drop, and then I should also hear the jet engine, right? But that will not happen. Why? Because there is a finite time over which it's actually seeing what is happening, picking up information what is happening after this. Okay, once it sees that, okay, I am trying to listen to the pin drop, but hey, some big signal is coming, okay, and therefore I am going to get hurt, right? So immediately this guy will soften himself, the muscles, okay, and therefore it will not even hear the pin drop, you will only hear the jet engine. Okay, so these are mechanisms, that's called pre-masking. So even though that event occurred in time, it will not be picked up by the ear. Okay, so these are protective mechanisms done by the ear, and sometimes we exploit it for compressing it, and anyway we can't hear it, so might as well throw away that information. Okay. So now I have talked about so I talked about the speech production aspect, and I talked about the speech perception aspect. So perception is where we talk about pitch, loudness, masking. All these are properties, Mel scale. All these are properties of the hearing part. Okay. So now I am going to switch back to how, given a speech signal, right? So I talked about speech signal, the production part, I talked about the hearing part. Now in everyday life, I am going to get the speech signal. How am I going to use the speech signal? What am I going to do? How am I going to process the speech signal to do something useful, right? One of the fundamental things we always do in most speech applications is this concept of something called Cepstral. Okay, so I'll describe what that is. Okay, so this goes back to the speech production model, right? So remember, there is an excitation that can be two types, voiced or noise like. That is the excitation part, and then the mouth, which acts like a filter, right? And different configurations of the mouth will give you different resonant frequencies, right? So that is what we are showing here, right? And so if you assume these are quasi stations over short intervals, this is a linear and a time invariant filter, then the input convolved with the impulse response will give me the output speech signal, right? But convolution in the time domain is nothing but multiplication in the frequency domain. Therefore, here I am showing only the frequency domain. So this is the excitation plot in the frequency domain. This is the resonant frequencies of the mouth for a particular sound in the frequency domain. Therefore, because these are frequency domain, we are passing through a linear filter, time invariant filter, they become a multiplication of these two. So if you see the envelope, right, the slowly varying part, the slowly varying part is capturing the aspects of the mouth configuration, right? These resonant frequencies will identify what sound I am producing, ah or e or oo, like that. This pitch is the vibrations that are there. Okay, so in many applications, I might want to separate out the effects of the sound, what particular sound, what phoneme or basic unit of sound that I am producing from the excitation aspects, right? How do I separate out? So I am actually interested in this signal, let us say, the mouth aspects of it, right? The resonant frequencies. But physically I can measure only the speech signal. Therefore, physically I am only getting this signal, which is a multiplication of this signal with this signal, right? And the Cepstral is a principle by which we can separate out these two guys. That is the basic idea. Okay, so I am going to now describe how I am going to do it. I'll explain to it by a simple example, and then you will see how I can. Okay, so let me just draw it for ease. Okay, so I'm talking about going back to filtering. Okay, so we are talking about filtering here, or separating two signals. Okay, let us worry about separating two signals. that are added to each other. Okay. So, if I have a signal like this, this is slowly varying in time. So, that means in the Fourier transform, it will have low frequencies. So, this guy will occupy a portion here which is low frequencies only. Okay, this is 0 here. Okay. Then let us say I have a noise signal. Oh, okay. So, here this is noise signal. Let me do this. Okay, so this is rapidly varying in time. Okay. So, it will have high frequencies. Okay. So, I can even put a different color if you prefer, right. So, it will be somewhere here. This is the noise and this is high frequency. So, let me call this as n of t. So, now if I add these two signals, let us say z of t is x of t plus n of t. Okay. Now, Fourier transform is what we call as a linear transform. So, the response will look like this. This y of omega will have this guy at 0, but it will also have these two guys. Okay. So, that is the basic idea of adding these two signals, right. So, now can I, given z of t, can I get back x of t? That is a question that we want to answer. So, just let me remind you, first we have a signal which is slowly varying, therefore, in the frequency domain this will be having a low frequency. Then we have noise which is rapidly varying and that occupies the high frequency region. Then we add these two signals. So, once I add, I only have access to z of t. I do not have individual idea of what x of t and n of t are. So, can I get, given z of t, the original signal, sorry, this is z of omega. Okay. Can I get back the original x of t? How can you do? We use filtering, right. So, we want to separate out. So, we use a filter here which basically, let me erase it. So, sorry, so that it looks better. So, it just line up there. So, this is a low pass filter, right. So, this is a low pass filter. If I do the low pass filter, then only this is actually x of omega, right, and these are the n of omega, right. So, this is n of omega, the noise part in the frequency domain. So, if I multiply the z with the h of omega, right, I get back a x of omega, right. So, that is what I am doing, right. So, x of omega happens to be nothing but z of omega multiplied by h of omega. Okay. This is the low pass filter. So, I can separate it out very well. Okay. This is an ideal filter. In practice, we do not do that. Instead, we do some kind of a averaging operation. So, for example, I can do x of t is almost going to be equal to x of t if I do an operation like this. Okay. I take z of t minus tau d tau, where tau goes from minus some t naught to plus t naught, okay, and let us say 1 by 2 t naught. You will, this is called an averaging operation, okay, and averaging operation generally will, so if you look at z of t here, how will it look like? So if you look at z of t, it will have the underlying slowly varying curve, but then there's noise on top of it, right? So there's noise. So actually it will look like this. This is how z of t is going to look like, okay? And what I'm doing here is a local averaging over a small interval of time. That's why I'm taking an interval. So around t, if you look at this t and this t, they are same. Around the t, I am taking some integration of those values and of course normalizing it and calling that as x of t, the low pass version, okay. So this is the practical implementation of the low pass filter, okay. And you will see that x of t will be almost similar to, it will be like almost similar to x hat of t. Sorry, x hat of t will be almost similar to x of t. That is what you will see, okay. So the low pass filter is a good way of, I mean averaging is a good way of low pass filtering, okay. So this idea you have to remember what I told you here. So given a slowly varying signal and a rapidly varying signal, they will luckily if they are quite well separated in frequency, then we can isolate the low frequency part of the signal, right, and by using a filtering operation, and a practical implementation of that is just an averaging kind of an operation, okay. So or if you are doing about samples, this x hat of n will be nothing but 1 by 2m plus 1 summation z of n minus m, where m goes from minus m to plus m. That is what it is, okay. So this is also an averaging thing, and if you look at it, this looks like a convolution, right. So this is almost like a convolution of, so x hat of n is h of m z of n minus m, okay. It almost looks like that, where h of m happens to be nothing but what, 1 by 2m plus 1 for m in the interval minus m less than equal to m and 0 otherwise. So this is how it looks in the time domain. So this is the low pass filter, and if you look at the frequency domain, it will be like this. This will be something called sinc function, okay, h e to the power of j omega. This is actually going to be periodic, okay, so you will not worry about it. So let me not confuse you with the periodic part, okay. So this is like minus pi to pi, okay, so minus pi to pi. This is almost low pass. This is how it's going to look like, okay. So these are practical implementation, something that you should remember, okay. So why am I telling you all of this? How is it related to speech? Okay, just recall that I have excitation E of omega, okay, then I have V of omega, okay, and speech signal is nothing but V of omega multiplied by E of omega, okay. This is the actual, this is the way I am going to get the Fourier transform of the speech signal. This is the Fourier transform of the speech signal. And the whole idea is, given S of omega, given S of omega, can we recover V of omega, okay. And the analogy is, given Z of t, can I get back x of t? Why am I saying this? Because Or I can also say, since S of omega equals V of omega plus, sorry, multiplied by E of omega, log of S of omega is equal to log of V of omega plus log of E of omega. This will be slowly varying. So, this log, the dynamic range now will become like this, okay, and this guy will be like this. That's what will happen. This is log of E of omega, this is log of V of omega. So, by V of omega and log V of omega have except for the dynamic range being smaller, exactly similar information. So, we are not worried about using logs, okay. So, still we get the information. So, the question now becomes, given log of S of omega, can I recover log of V of omega? And this is exactly analogous to given Z of t, can I recover X of t? This is slowly varying. This is rapidly varying. Okay, and they are added together. You can see that there is an addition here. So, the problem is very similar to what I talked about before. And how do I get rid of it? So, I take log of S of omega and then do some kind of a filtering, right, some kind of an averaging, right. And here, instead of this, in speech we can, so we can yes, we can recover by averaging or low pass filtering. But here already this is in omega domain. So, we do not call this as filtering because of omega and not t. We are not operating. So, filter normally means we are talking about time, but here the variable has become omega. So, usually they use, instead of filtering, okay, they use the term liftering. Okay. So, this is the term that will be used. So, we use a liftering, and this is basically what we do to get log of V of omega. Okay. And the whole this analysis using log S of omega is called Cepstral analysis. Again, this comes from spectra is from time to frequency. So, spec becomes Ceps. That is why it is called Cepstral analysis. Okay. So, these are terms just to remind ourselves that the variables, instead of time and frequency that we are used to here, we are actually going from frequency back to some kind of a time. So, this is the terminology that is used in speech processing. So, something that you should be aware. Okay. So, that I will again review it for 5-10 minutes, and with that we will come to a very important feature that is used in speech signal processing called Bell frequency Cepstral coefficient. And after that I am going to start with Gaussian, simple idea of what a Gaussian is, when the bell curve, then Gaussian mixture, then hidden Markov model, and so on. So, I will wind up of today's class, and we will start next class with a brief review of those Bell filters, Bell frequencies features, and then we will talk about the Gaussian and subsequently the Gaussian mixture model and then the hidden Markov model, okay, in the next 1 or 2 weeks or a few classes we will do that. Thanks.